Now I hear my things. All right, so tonight we're going to look at what's known as separatable equations. So this is basically the beginning of differential equations. I'm doing section 9.3 instead of section 9.1 and 9.2, as 9.1 and 9.2 basically look at how to figure it out from a geometric view and then how to figure them out from a numerical view. This is really the algebraic way to solve them, and one of the ways to solve them, because they're not all going to work out like this. But this is one of the ways that we can solve some basic differential equations. And this is just to give you basically a little preview of what differential equations the class will look like and deal with. So we're going to look at something known as separatable equations. Separatable equations are expressions for dy dx, which is the derivative, that can be factored into x and y. So I can pull the x's and y's apart and solve them independently. So that basically means that I can write g of x and f of y, or those two functions would be separate. So it doesn't make a difference how we write it. We can write it as multiplication, write it as division. It really makes no difference at all. Same thing when you have these with the fractions, we can cross multiply. So you have the hy dy equals gx dx. And then to take care of the derivative, we just do the integral of it. So it's basically working out what that equation is going to be in terms of y and x's. So once we start looking at them, which we're going to look at in a minute, the concept will make a lot more sense, because it's basically, instead of having just an equation with just x or just an equation with y, we have both variables in there, and they're not solvable for one of them. So, all right, let's look at one. So we've got the differential equations dy dx equals x squared y squared. And we're going to solve this one. So whenever you have a problem like this, the goal is basically to get all the y's on one side and all the x's on the other side. So we've got our dy dx, x squared, y squared. So I'm going to cross multiply these. So I'm going to have, this is going to become y squared dy, and then x squared dx. So this is why one of the times I said those dy's and dx's actually really come into play when you use them, because you actually can work at it with the dy and the dx instead of just having that be the derivative. All right. So now that we've got it solved for that, we're going to do the integral of both sides. So we're going to take the integral of y squared dy and the integral of x squared dx. So this becomes 1/3 y to the third equals 1/3 x to the third plus c. You only have to put the plus c on one side. If you did it on both sides, so here's the reason why, and I'll show you. So if we did the integral of y squared dy, the integral of x squared dx. So if I did, so it's 1/3 y to the third plus c1 equals 1/3 y or x to the third plus c2. And then I could bring this one over. So then I have 1/3 y to the third equals 1/3 x to the third plus c2 minus c1, which that right there is basically just a constant. Oh, and I wrote all that and I didn't flip over the screen. So there we go. So if we do the integral, we have c1 on this side, c2 on this side, and if I bring it over, I have c2 minus c1, which is no different than a constant. And since we don't know what the constant is, it doesn't make much difference. So that's why you only have to put the c on one side and you don't have to put them on both. And if for some reason you decide to put c on both sides and try to cancel them out, that doesn't work either, because then you eliminated the constant and we need the constant. All right, So once we've got it in this format, I need to solve for y. So if we can solve for y, if we can actually get the y by itself, you want to get the y by itself. Sometimes that's not going to be possible. And you would just leave it like it is. You wouldn't have to solve it out. But in this case, we can get the y by itself. So that's what we're going to do. So the first thing we're going to do is multiply the whole problem by 3. So I have y to the third, x to the third plus 3c. And then I'm going to take the cubed root of the whole problem. So y equals the cubed root of x to the third plus c. Because again, 3c is just still c. I can change letters and stuff like that, but it really doesn't matter. Any questions to where we are? All right. Now, in almost all these problems, if they truly want the original the equation, they have to give you a point to be able to figure out what c is. So in this problem, they originally told me that y of 0 equals 2. So we can plug that information in. So that would be the x and that would be the y. So I've got 2 equals the cubed root of 0 to the third plus c. So that means, so I can do the third of the whole problem. So I got 8 equals c. So that's now what c is. So then my final answer to this problem is y equals the cubed root of x to the third plus 8. And that would be the final answer. So the goal is that they gave you information to not have a c in the actual problem at the end. And that's a differential equation.
Oh, so said part B at the very beginning of the question.
Yeah, that was they gave you the initial condition.
Gotcha.
Yeah. Now, obviously, this integral was kind of simple to do. They're not always going to be simple to do. So, but all right. Let's look at another one. All right, solve the differential equation. Dy dx equals 6x squared over 2i plus cosine y. Same thing. We're going to do our cross multiplication on it. So I have 2i plus cosine y dy equals 6x squared dx. So then I'm going to do the integral of both sides. So I get y squared plus sine y equals 2x to the third plus c. And as shocking as this is, that's as far as I can go. That's actually the answer to this problem. Because there's no way to get y in this case completely and utterly by itself. So I can't solve it for y. And since it didn't give me a value to plug in to find C, I would leave the C.
So how do you make that determination? Just to be like, hey, that's as far as it goes here. I mean, wouldn't
So-
we technically solve just for X?
You could solve for X, yes. But most of the problems are in Y equals. So you could solve this problem for X if you wanted to, but you could not solve it as a function of Y, because we have multiple Y's here and there's no way to kind of put them together to get it by itself.
Is this a quadratic function in terms of Y? Or is it a quadratic geometric kind of weirdness?
Oh, yeah, this is just a messed up problem because it's got a trig function in it. It's got a cubic function. If you solved for X, you'd have a cubed root over Y squared and sine Y. Yeah, it's actually, I think I can actually graph this. Let's see. Well, I'll kind of be able to graph it. I'm going to make up a C because we don't have an actual C for this one. That's what it looks like. So really a weird problem. One of the cool things about Desmos is you can plug this stuff in exactly as you had it with the Y's and the X's, and it'll still be able to graph it out. So it's kind of cool to see what some of these equations kind of look like. So you can kind of see a quadratic in terms of the X type thing with it going that direction, but it then shoots off to infinity because it's the cubed root. And this has kind of got that sine piece in it. So this one, again, honestly, is not overly difficult to do, but it's got a little bit of a different thing in it. So I wanted to show you this one too. So this one's got that Y prime in it. Y prime is the same thing as saying dy over dx. That's the derivative in terms of x. So the derivative of y over the derivative of x. So that right there is dy over dx equals x squared y. So now on this one also, I don't necessarily have it in terms of two fractions. So cross multiplication isn't going to be as easy to do, but I can definitely bring my dx over to the side. And then I can divide the whole thing by y. So I end up having 1 over y dy equals x squared dx. So we still can get the y by itself and the x by itself. All right. So now I do the integral of both pieces. So this gives me an ln of y equals 1/3 x to the third plus c. All right, and in this one, we do have to keep the absolute value there. Because y could be positive or negative in this situation. So I guess the
Do we
next
make
question
everything
is,
like do we raise everything on the right side, to everything on the right side? Or can we not do that because of the absolute value?
that was actually going to be my question. So can we actually solve for y? And actually in this case, yes, we can solve for y by basically taking the entire problem and raising it, putting it up in the e. So that'll be the exponent. So e and ln kind of cancel each other out. So this side is just the absolute value of y. And this side becomes e x to the third over 3 plus c. Now, I'm not going to want my constant up inside the piece there. So if we can pull up the constant, that's going to be nice. Remember that when you're adding exponents, that's really the same thing as if you multiply in the bases are the same. So this problem is going to change from the absolute value of y to EC, and then e to the x to the third divided by 3. So with those multiplied by each other. All right. To get rid
Why was
of
that first? Why was the
Okay.
first answer improper? Why'd you break them apart?
Because we kind of want to we want our constant just to be a single letter. So this way, if we're going to solve for it and things like that, it makes your life a lot easier. So remember, a constant's a constant. So the problem with it being up in top here is it's still e raised to that power. So I kind of want to pull it out so it can be its own actual constant. So that's why splitting it up like this allows me to take that part right there and make it an actual constant, which is what I'm about to do in the next step by changing the letter. But the other thing that we have to do is we have absolute value. So absolute value just means that it's the plus and the minus just disappear. So technically, this side can be either one of those. So this is going to be plus or minus. I'm just going to make this a random letter. We'll use A, because I don't really want to use C in this situation. So this would be my final answer. So it doesn't matter what the constant is because it's still a constant. So I can use any letter to represent it, but I don't want to get rid of the E in that situation. So we don't have a constant inside of something else. Does that make sense? Or is there any confusion on it?
Yeah, so the e to the c becomes a, like,
Yeah.
and the plus minus is the result of us getting rid of the absolute value, right?
Yeah.
All right, just making sure.
All right. Skip that problem for a second. I want to do a couple more. Just a couple more simple ones before we do the more complicated one. I star. All right, so we've got this problem. So let's look at it. So if we cross multiply these, I've got ut squared plus u to the fourth t squared du equals 1 plus t to the fourth. I'm going to totally change this because I don't like the t's. They look like pluses. I'm going to make the t's x's just to, so I'm going to change this. So du over dx. So it's 1 plus x to the fourth over ux squared plus u to the fourth squared. So we cross multiply this one. I get ux squared plus u to the fourth x squared du equals 1 plus x to the 4 dx. So what's the problem in this one? Can I do the integral of both sides now?
No, you still got U's.
Yeah, I still got u's with x's. So that can't happen. So we've got to figure out some way to be able to deal with that. So in this problem, the way it's set up, now, and there's some situations that you wouldn't be able to do it. And we'd have to use a different method to do it. In this situation, though, I can factor out the x. So I can take out the x squared. And then I can divide both sides by x squared. So now I have u plus u to the fourth du equals x to the negative second plus x squared dx. And the reason I didn't leave it like a fraction here is because if it's a fraction, that means I have to do more complicated integration for it. If I can make it just individual terms, I can use the simple integration process for it. And in this case, I was able to break it up and do the simple way for it. All right. We're at this. Now let's go through and do my integral. So I can do my integral of both sides. So I have u squared over 2, u to the fifth over 5 equals 1 over negative 1 over x plus x to the third over 3 plus 3. Can I solve this for you? So the only way to solve for u is if I could get those two u's to be 1 u. And in this case, you really can't do it. So that would be the final answer. And in this problem, they did not give you a value for the function to be able to find c. All right. One more of these, and then I'll do the horrible word problem. Well, I'll do the application problem. That's where we actually would use this. All right, so this one's got the y1 equals 1, so we're going to be able to find c for this problem. The way that it's set up, do I have a dy and dx? I do, my dy and dx are right here. So that's dy over dx. So that means I in essence have x ln of x dx equals y1 plus cube root of 3 plus y squared dy. So we're going to do the integral of both these sides. All right, so let's look at these separately. Let's do the integral of x ln of x. So how am I going to solve this one?
Chain rule.
Can't do the chain rule because I'm not doing derivatives.
Oh, okay.
But what is the mirror piece for the chain rule in integration?
Like a U substitution or
Yeah, it's actually integration by parts.
okay.
So we're going to do integration by parts. So u du and v dv. So which part do I want to make my u? Do I want to make it the, so I've got x and ln of x. The question is, which one's going to be my u?
ln of x.
Yep, because remember, logarithms are always first. So that means my du is 1 over x dx. And then dv is x dx. So this will be x squared over 2 for that. So I have x squared over 2 ln of x minus the integral of x squared over 2 times 1 over x dx. So I've got x squared over 2 ln of x minus 1/2 the integral of x dx. That would be the integral for the x ln of x. All right, let's look at the other side. What's the first thing we want to try in this one?
Do you want to
Did you
distribute the y
substitute?
first?
Yeah, let's distribute the y. This way it gets rid of my parentheses. So I have y plus y cube root of 3 plus y squared dy. All right, so the integral of the first piece is really simple, right? That's just y squared over 2. Now, the integral of the second part, what do we want to do with that one? So if I'm just looking at the integral of y 3 plus y squared. I'm just looking at that. What do we want to try?
You so?
All right, what am I making you? Whenever
Do
you're
we
looking
need
at
to
your
be-
substitution, pick you to be the thing that's annoying you. What's the piece of that problem that would be annoying?
the extra y dy. Or do you to try to get rid of it? No.
So my goal would be, so du would end up being something y dy, right?
Mm-hmm.
That would be my goal. However, but the thing that's really annoying if that wasn't there would be that piece. So if I make my y that, dy is going to be 2y dy, right? So I have 1/2 du equals y dy. So this problem, when I substitute back in, I have, I'll call it the 1/2, and I've got u to the 1/2 power. So that's going to be 1/2 times 2/3 u to the 3/2. So we've got plus 1/3 3 plus y squared to the 3/2 for that part. Okay. Any questions with that one? We're still not done with the problem, but we're getting there. All right, so this would be what my integral is. I have the x squared over 2 ln of x minus 1/4 x squared. I put the c on my x side. It doesn't really matter which side you put it on. I just always put it on my x side. 1/2 y squared plus 1/3, and then 3 plus y squared to the 3/2 power. All right, now in this problem, they gave me information to find my c. So first thing is, can I solve this for y? Looking at this problem. Probably not. So we're going to plug in, so that would be my x value, that would be my y value. So let's see if we can figure out what c is going to be. So I've got 1/2 ln of 1 minus 1/4 plus c equals 1/2 plus 1/3 times 4 to the 3/2. So ln of 1 is what?
0.
Right, so that's gone. I can move my 1/4 over to the side, so I don't have to have both sides. So C equals 1/2 plus 1/4 plus now 4 to the 3 halves. Square root of 4 is 2 to the third is 8. So that's 8 thirds. Which equals 41 over 12 is my C. Then we just plug it back into the C. So the final answer looks like that. All right. All right. Last one. Let's do a word problem. Because there actually is some application to these. All right. So we've got a tank of salt that contains 20 a tank contains 20 kilograms of salt that's dissolved in 5,000 liters of water. The brine that's entering contains 0.03 kilograms of salt per liter of water that enters the tank, and it enters at a rate of 25 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. So there's never going to be more than 5,000 liters of water in the tank. How much salt remains in the tank after a half hour? All right, so what am I looking for in this problem, basically?
How much salt ends up being after half an hour? It's a change over time, probably.
Right. So in essence, we're going to have, so we're going to use dy over dt, where y is salt. Because that's going to be the thing that's changing. So that's, in essence, going to be my rate in minus my rate out. Correct? So let's look, we got to figure out those two basic equations and then we can put them together to do the actual problem. So let's look at our rate in first. So how much salts or how much, what, and the stuff coming in, how is it coming in? So it's 0.03, right? kilograms per liter. That's the salt that's coming in, correct? And that's in 25 liters per minute. Does that make sense? And the actual units are actually matter in this situation. So that means every minute I have 0.75 kilograms per minute. Does that part make sense?
Yeah, it's good.
Now let's look at our rate out. So the amount of salt going out, do I know? So going out, I'm not exactly sure. So we're going to call that Y. But I do know there's 5,000 liters in the pool. That's kilograms over liters. And I
Great.
still know.
How did you figure that out from the language there? All we get is drains from the tank at the same rate, which we just
Right,
figured out
so-
is kilograms per minute.
So we know coming in, there's a brine that's 0.03 kilograms per salt per liter, right? So, but going out, I don't know how much salt's in the tank at any given time. I know there's 5,000 liters in the tank. I just don't know how much salt's there. So that's why we pick a variable Y. You could use technically any variable you want, but we're going to use Y. Because we're just not
Okay,
sure.
so we know how much salt is coming in, but
Right.
how much salt is coming out is going to be, well, we got to add the 20 kilograms per 5,000 liters, right?
Well, yeah, because we got to remember, as that the brine's coming in, the amount of salt that's in the tank changes. So coming out wouldn't be the 20 kilograms of salt, because after 1 minute, there might not be 20 kilograms of salt in the tank. It might be more, it might be less. So, and that's the thing, is like we're not sure what the actual salt content of the tank is at any given moment right now. We're gonna know soon because we're gonna figure it out. But right now, I don't know because they don't give me that information. So when they mix it all up, the water that's coming out the bottom of the tank is going to have some amount of salt in it. I just don't necessarily know exactly how much salt it is for that 25 liters per minute, which is the other part here. So my rate out is then going to end up being Y over 200 kilograms per minute.
Because it's, oh, I see, I see. You multiply it simply because we're already at rate out, so we don't need to make it a plus or minus because the whole thing is already rate out. So it's going to be
Right, yeah.
minus 0.
Yeah, when I put the actual problem in the equation, which we're going to do in a minute, we'll have the subtraction in there. So this is my rate in, this is my rate out. All right. So everybody good finding my rate in and my rate out? Notice the units are both the same. It's kilograms per minute. So when I'm writing the next step of the problem, I'm not going to put in the kilograms per minute. We just know that's my unit. So this is now my equation. This is my in, and that's my out. So we got to make this kind of nice. So it's really nice when we have a fraction on both sides. So let's rewrite this equation a little bit. So I can make one denominator there. So I have dy over dt. So I'm going to multiply the first one by 200. So I have 150 minus y all over 200.
Why didn't we account for the original 20 kilograms of salt?
Because that has nothing to do with the rate in and the rate out. Really what this problem right here is doing is this is telling me how much the salt is changing in the tank. When we go to, once we get our final answer and we have the C, we're going to use that 20 as the constant piece to find the actual C to come up with the equation of actually how much salt in the actual tank. This equation that we're looking at right here is just telling me the change in the salt in the tank.
But the volume remains the same, is what you're saying.
Right, the 5,000 liters of water stays exactly the same no matter what, because it's coming in and out at the exact same rate. And that's actually really important in this problem. If it didn't come in and out at the same rate, we also wouldn't know the 5,000 there. And that would be another variable that we would have to account for. By having the rate in and out the same, the actual water in the tank, the amount of water in the tank stays the exact same. All right, so we've got our differential equation. So now we've got to get it so that I've got my y's on one side and my t's on the other side. So and this one, basically all we're going to do is we're going to switch those two. So I have dy over 150 minus y equals dt over 200. And then we'll have our integral on both sides. The 200 actually doesn't matter. If I put it on the other side, it wouldn't have made a difference. All right. So this side here, if we're looking at, let's look at this piece over here. So I've got the integral of 1 over 150 minus y. So if I make my u 150 minus y, my du is negative dy. So this is the integral of 1 over, or negative 1 over u du. So it's negative ln of u, which is negative ln of 150 minus y. And this side is just 1 over 200 t. it doesn't look like a plus. T over 200 plus C. All right. So we good to that point? All right, so now we have information. So we can figure out the C. So here's my integral or my differential equation. And I know that y of 0, when time is 0, there was 20 kilograms of salt in the tank. So if we plug 20 into this, I can figure out what my C is going to be. So I have negative ln of 130 equals C. So my equation is negative ln 150 minus y equals T over 200 minus ln of 130.
Is this saying like y at time 0?
Yeah, that was what the equation, that was what it was. So y times 0 is 200. I mean, this point, sorry. Because that's what that first part right there was. So at the beginning, I had 20 kilograms of salt in the tank. So now this equation is going to give me how much salt is in the tank at any given time. That was what we were finding. Originally, we had how much we were looking for. The rate in and rate out was the actual time, the change in salts over time. So that's why it's a derivative, because it's the change, it's a slope. What we're getting from that is actually an equation that's telling me how much salt is in the tank at any given point. And that's where the 20 comes into play, because I needed to understand what was there at the beginning.
I'm still confused as to how we got y of 0 is 20.
So remember, y was basically my how much salt was in the tank at any given time, right?
Oh, so time is equal to 0. That's the start.
Right.
Okay, sorry. I got you now.
That's okay. All right, so we're not done, because that wasn't actually the question of the question. The question wanted to know how much salt remains in the tank after half an hour. So at the beginning, there was 20 kilograms of salt in the tank. After 30 minutes of doing this, how much salt is in the tank? So we really want to know y of 30 equals something. So the only way to do this easily is to actually get the equation solved for y. So we're going to take this equation and we're going to solve for y. So first thing I have to do is raise everything to the e.
Wouldn't you have to multiply everything by -1 first?
Yeah, I could do that. I could still have e raised to a power, but yeah, I could do that. Either way, it works. I guess multiplying it to -1 is going to save me one extra step at the end. So, All right, so let's change everything, basically all the signs. Now we'll raise everything to the E. So I've got the absolute value of 150 minus y equals e to the negative t over 200 plus ln of 130. So since y is never going to be less than 0, I don't necessarily need my absolute value symbols here, so I can get rid of those. And e to the ln of 30 is just 130. So and then I can move over my 150 and change all my signs again. So y equals 150 minus 130 e to the negative t over 200. And then we're going to plug in 30 for t, because now this equation will tell me the salt in the tank at any given time. So we have equals 150 minus 130 e to the negative 20 over 200.
But it was 30 minutes.
30. Yeah, half hour. So we get approximately 38.1 kilograms of salt. Is in the tank after 30 minutes. So the amount of salt in the tank is increasing. So actually, if you left this as X, we can actually see how much salt in the tank at any given point.
So based on the given for language, though, I mean, the math makes sense, but I feel the given language is super vague because they say, so the solution is kept thoroughly mixed. Okay, kind of pointless statement. Drains from the tank at the same rate, which is like, okay, of 25 liters per minute. But at the same rate could also be construed as at the same rate as exactly what we figured out, which is 0.75 kilograms per minute. So to kind of make that decision, like, oh, they mean 25 liters per minute and not 0.75 kilograms per minute, I think is like, it's a brutal wording.
Yes, however, there's one piece of information in this problem that you dismissed that actually is very, very important to this problem. So if you're thinking about how water would flow, water is going to come into the top and come out the bottom. It's just the way water is going to flow. It's like it can't come out the top because it's not going to flow that way. So if the brine's coming in the top at 0.3 kilograms at 25 liters per minute, so 0.75 kilograms per minute of salt's coming into the tank. If it wasn't mixed thoroughly and I was draining out the bottom, the water at the bottom would be my original concentration of salt.
Okay.
By having it mixed thoroughly, that brine that's coming in, now the water is a consistent level of salt at any given time. So that's why we don't know how much salt's coming out, because at that point, once we start it, I don't know how much salt is actually in that tank. So there's no way to say, oh, 0.7 kilograms of salt's coming out because just water's coming out. I don't know how much salt's coming out because it's mixed into the entire thing. So at any given point, I'd have to figure out exactly how much salt is in the tank to determine how much coming out. That's why it's a derivative. That's why we have to use calculus for this, because we have to determine at any given moment how much salt is in that actual tank. That make sense?
Yeah.
So the rate was really just depending on how much water, like, of the mixture was coming out. All right, that's it.